Okay, so here's our Chapter 9 review. So it comes down to kind of four general areas. One is convergence tests. So we have that table with all the different tests. And we went through that big handout looking at all those different tests. Then you have radius of convergence. And interval of convergence. So that was applied to infinite series where x is the variable. We got to figure out which values of x this infinite series converges for. Then there was the Taylor polynomials, but we're just going to talk about either Taylor series or Maclaurin. I can't exactly remember how to spell Maclaurin. So this is how we generate infinite series to approximate or to equal functions. And we also looked at this same kind of deal of deriving what the infinite series are from the result that the summation from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r. Okay, so those are the different areas. So the basic concept of the problems associated with the convergence test is I'll tell you which test to use, so you don't actually have to worry about that. So I'm sure you're happy about that. The question is you'll have to use whatever the convergence criteria are for that particular test to prove that the series converges or diverges. And you'll have to write something out. We went through that in detail in that handout again in class, so you should kind of go back and review that, maybe write down one example to give you an idea of the terminology. And the types of series, well, I'll tell you which ones you don't have to worry about. So there will not be a telescoping, so these are the ones you don't have to worry about. Telescoping series. Let's see what else. One that you might not need to use. Actually, I think that's the only one that is not on the test. Is telescoping series. So I'm just going to give you a few examples. I'll talk through it. I'm not going to write it out. You can look at your work you did in class. But let's say I give you a series like this, and I have, say, 9 divided by okay. So if we had like 3 to the n power, okay. So this is, first you have to identify, well, I would tell you it's a geometric series, so you'd have to just do a little manipulation here to rewrite it. And remember, you can always put a 1 in the numerator like that, because 1 to the n power is 1. 1 to any power is 1. So this is really that. And now it fits the form of a geometric series. So you would say something like since this is a geometric series, with r equal to 1/3, which is less than 1, the series converges. According to the convergence criteria. Of the geometric series test. It also converges to S, which is the sum equals A divided by 1 minus R. And then you would look up and find that A is 9 and R is 1/3. So that would be 9 divided by 2/3. If you take the reciprocal at the denominator, it's multiplying by 3/2, so you'd have 27 halves. Now that's the only one of the series tests that we can actually give a value, except for the telescoping series, which I'm not going to ask you about. So that would be an example of something like the geometric series test. Like I said, I'm not going to do every one of them. You can go back and review that handout, but I'm going to do one more for you. So let's say I have something like summation from n equals 1 to infinity of 1 divided by n, say to the 3/2 power plus n. Okay, so in this case I would probably ask you to use the limit or the direct comparison test. So the direct comparison test is you find a function b sub n that is going to be always less or always greater than a sub n, and if b sub n converges, then we know a sub n converges. You can also do the other way. If if you picked an a sub n or b sub n which is always less than a sub n, and b sub n diverged, then a sub n would have to diverge. So in this case, a sub n is just the expression I have here initially, and the second one would just be 1 over n to the 3/2 power. So to be able to use the direct comparison test, the only thing that you need to prove is that a sub n, well, that a sub n is always less than b sub n for all n. Really, actually, it's as n goes to infinity, but because you could just have the first few terms different than the rest of them. It's not the first few terms that make something go to infinity, it's the infinite number of terms. So let's prove that's true. Or we could, so how would we prove that's true? Well, if you well, you can tell they're positive because n is always positive. And then you could actually write in the expressions n to the 3/2 plus n, is that always less than or equal to 1 over n to the 3/2 power. So you cross multiply, you get n to the 3/2 power. Is that always less than this cross multiplication, n to the 3/2 power plus n? Well, you can see those cancel out with each other. So you get, is 0 always less than n? Well, n starts at 1 equals 1, 2, 3, 4, so this is true. So this is always true. So hopefully this converges, and in some ways you'd actually choose this to know it's going to converge. So once you've satisfied that, then you look at the convergence of B sub n. So I would say, B sub n is a p-series with p equal to 3/2, which is greater than 1. And if you look at the criteria for a p-series, if p is greater than 1, which it is, this series, so B sub n converges according to the p-series test. And then you would then be able to finally write something like, since A sub n is always less than or equal to B sub n, and B sub n converges, the series summation from n equals 1 to infinity of 1 over n to the 3/2 power plus n also converges according to the convergence criteria of the direct comparison test. Okay, so that's the first topic. The second topic is going to involve interval of convergence and radius of convergence. So usually in those cases, to make it more interesting, a lot of times it's an alternating series. Sometimes it has some number raised to a power, kind of like a p-series. And then there might be something involving n, or n plus 1, or n plus something. And then you might have what else might you have? You could have a factorial or something like that in there. A lot of times factorials end up being converging for all real numbers. So again, we had that handout that we worked through 3 different examples, so you can go back and look at that as well. But the concept here, let's talk about the concept, is you've got the original, we'll call it u sub n, which is negative 1 to the n power 5 to the n power over n plus 1 n factorial, and then you create this u sub n plus 1. So you take every term here that has n and you change that to n plus 1. So n plus 1 becomes n plus 2, and n factorial becomes n plus 1 factorial. And then you use the ratio test. And the ratio test from a series standpoint says that the limit so the ratio test for series involves a sub n plus 1 over a sub n for a infinite series that involves x, which I didn't put in there, so that's what I need to do. I knew I was missing something. So let's say we have x to the n here instead of 5 to the n. We could have a, 2 to the n down here. So you'd have x to the n and a 2 to the n. So let's go ahead and fix that. So this would become x, and this would become 2 to the n plus 1. So what you do is you take the limit of u sub n plus 1 over u sub n, and for this to converge, that has to be less than 1. So we'll plug in u sub n plus 1 in the numerator of this fraction. And then we plug in u sub n in the bottom. And that has to be less than 1. Again, the idea is to figure out what values of x does this series work. So what we do is we take each one of these terms and we create an individual fraction so we can ultimately simplify them. So we've got negative 1 to the n plus 1 divided by negative 1 to the n. In the numerator here we've got x to the n plus 1 divided by x to the n. And here we got 2 to the n plus 1 in the denominator, so this 2 to the n goes to the numerator. We've got n plus 2 in the denominator here, so that means this n plus 1 is in the numerator. And then finally here we have n plus 1 factorial. Here we've got n factorial. So here you just get negative 1. X to the n plus 1 over x to the n is x. 2 to the n over 2 to the n plus 1 is 1 over 2. Here we don't have anything we can simplify. And in this case we have n factorial, and n plus 1 factorial can become n plus 1 times n factorial. And that all has to be less than 1. Now when you take the absolute value, that is irrelevant, and remember what we're doing is we're taking the limit of this whole thing as n goes to infinity. So this should be a limit thing out in front. Same way here, limit. So when we take the absolute value of negative 1, it just becomes positive 1. Here we have x, so we'll have x over 2. When you take the limit as n goes to infinity, that becomes 1. And that simplifies out. You get 1 over n plus 1. And because of the factorial here, you can see that as n goes to infinity, if you take the limit as n goes to infinity, this is going to go to 0, because this part's going to go to 0. 1 over infinity is 0. And so it doesn't matter what x is. So for this particular case, the interval of convergence is between negative infinity and positive infinity. The other options, the more likely options to be on the test, are where we don't have a factorial. So what would happen is instead of having this term, we'd get rid of that term. So let's just do the whole thing without the factorial. So cross that out, cross that out, cross that out. Don't have that, don't have that. And so these two terms go out. And so then what happens is you would end up with this situation. So under those circumstances, you end up with the absolute value of x over 2 is less or equal, there's less than 1. So you'd multiply both sides by 2, or actually what you do is you create this type of inequality. So you go from -1 to +1, then multiply by 2. So this would be my radius of convergence would be 2, because I go from the center, which is x equals 0, plus 2 and minus 2. So that's my radius of convergence. Then you'd have to evaluate the endpoints. And the endpoints are x equals -2 and x equals +2. So you plug those into your original expression, which is this thing. So let's just grab that and bring it. Okay, so that's the expression. So you'd have a summation from n equals 1 to infinity of -1 to the n times, and this was x. So I'm going to fix that. Okay, it's x to the n. So you put in x equals -2. I'm missing something. What is missing here? Oh, because I added this extra term. Yeah, there's a 2 to the n thing in there. Put that in there. 2 to the n. And this, let's make sure I got that right now. -1 to the n, x to the n. Okay. -1 to the n, x to the n of 2 to the n over n plus 1. Look at that, -1 to the n, x to the n over 2. Okay. So now you plug in x equals -2. So you'd have -2 to the n divided by 2 to the n times n plus 1. And you can take the -2 to the n and break that up into 2 parts. So you'd have -1 to the n times -1 to the n times 2 to the n divided by 2 to the n over n plus 1. So that becomes these 2 parts. So you see the 2 to the n's cancel out. So I have the summation from n equals 1 to infinity. -1 to the n times -1 to the n is -1 to the 2n divided by n plus 1. Well, -1 to an even power is positive, so this just becomes the summation from n equals 1 to infinity of 1 over n plus 1. And what would happen in this case, you could use the limit comparison test, you could use the direct comparison test, but what you'd find out is that diverges. You have to spell out what the convergence criteria is for that particular series. And that's when I plugged in this endpoint. Now if I plug in the right endpoint of -1 to the n, 2 to the n divided by 2 to the n times n plus 1. Well, I don't have to do anything to cancel those out because they're already the same. So what that leaves me with is this, which is -1 to the n times 1 over n plus 1. So this is an alternating series. And the requirements for an alternating series to converge is the summation from n equals 1 to infinity of a sub n equals 0, which it does. This is a sub n. 1 over infinity plus 1 is 0. So that works. And the other one is that a sub n plus 1 is always greater than or less than a sub n. So if I put in a sub n plus 1, which would be, what you do is you plug in n plus 1 to here, and then we add, so we have n plus 1 plus 1. Is that always less than 1 over n plus 1? So you get 1 over n plus 2. Is that always less than 1 over n plus 1? Cross multiply. N plus 1 is less than n plus 2. 2's cancel out because they're in both. 1 is less than 2. Yes. So that's true for any value of n. So we know that's satisfied for the alternating series test. And so because this series, which is evaluating the original series at x equals 2, if that converges, then the whole thing converges. I mean, the endpoint converges. So ultimately, when we come back to our interval of convergence, we put a equal sign on this side, but not on that side. So when x was negative 2, it diverged. When x equals 2, it converged. And so that's your final interval of convergence. Okay. Okay, so the third item is to do either a Taylor series or a Maclaurin series derivation of an infinite series. We did a couple of these in class. We did the sine of x, I think. We did e to the x, where we took this function and took multiple derivatives. We also did things like 1 over 2 minus x. So these all come down to the Maclaurin. So this is Maclaurin. It says there's a, well, if you use a Maclaurin polynomial, it's p of x, but for a Maclaurin infinite series, it's equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus so forth and so on. So that's the Maclaurin. The Taylor series is going to be at some value x equals c. So you do f of x, still f of x, but it's around, instead of around x equals 0, which is what happens here, is you have f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared divided by 2 factorial plus f triple prime of c at c times x minus c cubed over 3 factorial, and you keep doing that. So rather than do ones that we've done before, let's say I wanted to, let's say my original function was 1 over x squared, and I wanted to come up with a infinite series to represent 1 over x squared. And I'm going to do it around c equals, say, 6. Because if I did around 0, you know, it's undefined at 0, so it probably wouldn't work out too well. Now, what I can do is rewrite this as x to the minus 2 power. So the first derivative is going to be the exponent, negative 2 times x to the minus 3 power. And the second derivative is going to be, so I'm going to do all these derivatives and then I'll rewrite them back. So this will be negative 3 times negative 2, which is 6, x to the minus 4 power. And then f triple prime is going to be equal to negative 24, x to the minus 5th power. And the fourth derivative is going to be 120, positive 120, negative 5 times negative 4, x to the minus 6 power. So let's That's right, this is negative 2 over x cubed. This is 6 over x to the 4th. This is equal to negative 24 over x to the 5th. This is 120 over x to the 6th. So if we wanted to write the f of x, we need to evaluate these at 6. C equals 6, so that's actually going to be negative 2 over 6 cubed. This would be 6 over 6 to the 4th. It's going to be negative 24 over 6 to the 5th power. This will be 120 over 6 to the 6th power. So because this is a Taylor series, because we're going around some value other than x equals 0, we're going to have, it's going to be f of 0. So I didn't put that in there. F, not f of 0, but f of 6. So in this column I also have 1 over 6 squared. Okay, so the first term is 1 over 6 squared. The second term is negative 2 over 6 cubed times x minus 6 plus 6 over 6 to the 4th power times x minus 6 squared divided by 2 factorial. And then we have the next term, which is negative 24 over 6 to the 5th power times x minus 6 cubed. Is that right? I think so. You see is 6 squared, 6 cubed, 6 to the 4th, 6 to the 5th. Let's add one more term. 120 times, we got to divide by 3 factorial. So this is x minus 6 to the 4th power over 4 factorial. Bop, 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 bop. Now the question is there any way we can simplify this a little bit? Or if we could come up with the equation. I'm not going to ask you to come up with the equation, but I'm going to see if I can figure it out. I'm just going to ask you to get the terms. And I just leave it as this, leave it as factorial. So we're going to start at probably 0 to infinity. We're going to have negative 1 to the 0 to the n power, so that when n equals 0, we get that. And then you're going to take 6 raised to the n plus 2 power. So when n equals 0, this is even. This negative 1 to the 0 power is 1. When n equals 1, you get negative 1 to the 1st power, which makes it negative. So this makes it alternate. You're going to have x minus 6 raised to the n power. So when n equals 0, x minus 6 to the 0 power is 1. X minus 6 to the 1st power is x minus 6, and so forth. So that gets taken care of. And then in addition to this 6th thing, you're going to have n factorial, I think. So here n factorial, 0 factorial is 1. Here 1 factorial is 1. 2 factorial is 2 factorial. 3 factorial is 3 factorial. So that would be the actual equation form, and then we could look at the interval of convergence. Because this is factorials in there, there's a good chance that it might work for all real numbers, possibly. So anyway, that's what we're talking about. I might give you, ask you to do a Maclaurin series. That means C is 0. I might give you one of these that we did in class, which were the e to the x and the sine of x, or cosine of x would work. I could give you something like that. Okay, and the last one is one we've just worked on in class, is this case of where you're given a function that looks, say, something like that. And the whole idea was to rewrite this to get it to look something like a over 1 minus r. And then you could use this result to deduce what the infinite series was in terms of a geometric series. So the first thing we're going to do is we want to get this so that you have the negative sign associated with the x. So if this is positive instead of negative, if it was 3 minus x, we'd be great, but we have x minus 3, so you're going to factor out a negative sign, so it'll be 3 minus x. If it was already 3 minus x, 5 over 3 minus x, we could skip that step. Ultimately, the first step is to change the denominator to a minus x, and the second question is, what are we going to do this around? What number? So let's say if I pick 5, around c equals 5. So we need this to be x minus 5. So whatever number we are centering the infinite series around, that's this part. So this number here is that number there. So first thing is get the negative here. If it means factor in a negative sign, do that. So now we set the denominators equal to each other and solve for a. The x parts cancel out, so you get 3 is equal to a plus 5, or a is equal to negative 2. Okay, so this now becomes negative 5 divided by a, which is negative 2, minus x minus 5. If I did that all right, I should get back to here. So, if I negative 2 plus 5 is positive 3, and I'll have negative x, so I'll have 3 minus x, and then if I multiply it by negative 1 in both the numerator and the denominator, we're in good shape. Okay, so that's the first step. The second step is to make it so this is a 1. So the way we do that is we're going to factor out the negative 2 in the denominator. So that'll leave 1 here. Whatever this number is what we factor out. And if you factor out a negative 2 out of this one, you'll get, the sign will change, so you get plus 1/2. So we divide by that. We divide this by that number, and we multiply by x minus 5. Again, it's the same as the original expression. This should be the same as that if we multiply it out and simplify it. So let's just go back one step. Negative 2 times 1 is negative 2. Negative 2 times positive 1/2 is negative 1 times x minus 5. Okay. Final step is we're going to put both of these constant terms in the numerator, well, next to final step. So we get negative 5 over negative 2 divided by 1 plus 1/2 times x minus 5. So our final equivalent expression is 5/2 divided by 1 plus 1/2. Plus 1/2. So one more step here is we need this to be negative 1 minus r. So it's going to be negative 1/2 times x minus 5. Okay. Again, this should be exactly the same as the original expression. So what we know is a is 5/2 and r is equal to negative 1/2 x minus 5. So what we said was a over 1 minus r is equal to the summation from n equals 0 to infinity of a times r to the n. So now that we have A and R, we can plug them into there. So our infinite series is going to be equal to A, which is 5/2, times R, which is -1/2 x minus 5 to the n power. So what we can do now is we can take this -1/2, make that to the n power, and x minus 5 to the n power. Then we can factor out a -1, so we'll have -1 to the n, and then we'll have 5/2 to the n times 1/2 to the n times x minus 5 to the n. That's not exactly true. Okay. We will have, so 5's not to the n, you have 5. And what we have is 1 to the n, and we'll have 2 to the n times n, so that's 2 to the n plus 1. So that's how the negative comes out as this alternating term. 5 is by itself, so it doesn't get an exponent. 2 is in the denominator, so it's 2 to the n times 2 to the n times 2 to the first power. You add the exponents. So ultimately the final answer here is -1 to the n, and so the 5 can go in the numerator here. 1 to the n is just 1. We get 2 to the n plus 1. I think I messed up. I put this on here. Didn't need to put that. That's combined. So we get 1 to the n, 2 to the n plus 1, okay, times x minus 5 to the n. And that's the final answer. Okay, let's go back through it, make sure we did everything right. Make sure you understand each step. Be clear about it. If you can't follow it through, then you've got to put some extra notes in there. So we start with this expression. We want to get to this point. So what I do first is I factor out a negative sign. So we get a negative here, and these change signs. I want that equal to -5 over a minus x minus 5. The 5 that I'm subtracting here comes from where I'm centering the series around. So we set the denominators equal to each other. The x parts cancel out. Solve for a, you get -2. So now I can plug -2 into that, and I get this expression. Then I can factor out a -2. So when you factor out a negative, it's this number you factor out, so that always becomes 1. And to factor out a -2 here, I'll get a positive 1/2, meaning I'm dividing by 2. Again, each step you can go back and check. If you go back one step, make sure it works. And I'm just checking it right now. It does work. Combine these two terms into the numerator, simplify. And at that point, now I have a over 1 minus r, but to get a minus r, I have to make this a negative, which means I have to multiply this by a negative sign. So you'll end with the negative times the negative to get the positive. Again, I'm going back one step to make sure I'm doing everything right. Okay, so I now identify a as the numerator, r as this term. And then I say, well, if I have a over 1 minus r, then that must be represented by this geometric series. So then I stick in a and r. I take this constant in front of x minus 5, and I raise that to the n power, and that one, so I break it apart into 2. Then I take the -1 and I put that separately. what that leaves me left with is 5, 1 to the n divided by 2 to the n, but also multiplied by 2 again, so it becomes 2 to the n plus 1. 1 to the n is just 1, so that disappears. So you just have 5 times 1, which is 5. 2 to the n plus 1, and that should be negative 1 to the n, and that comes down. So this term, x minus something, is always, this number is always the number that it's centered around. I don't know where this 2, let's see if there's any, go back to the original thing, where 2 might have been. Well, you don't even see 2 in the original. 2 comes from here. Okay, so that's it. Make sure you know how to do all the convergence tests. Calculate the interval of convergence and the radius of convergence given this particular infinite series. Figure out the infinite series for a function. Could be a trig function, could be e to the x, could be just a rational function. And then finally is to use this geometric series approach to take something like this and convert it into a over 1 minus r, and then go back one step to then predict what the series would have to be to get that result, and then do some simplification here to get to the final answer.